Okay, so welcome everyone to the final MLFL, and thank you so much for joining us. This week we're very excited to host Kelsey Allen, who is a PhD student at MIT, advised by Josh Tenenbaum in the Department of Brain and Cognitive Science. Her work has been awarded with an NSERC PGS doctoral fellowship, and she's also won a Best Paper award from Robotic Science and Systems. Before coming to MIT, she studied physics at UBC, where she contributed to papers on particle physics at the Large Hadron Collider, as well as collective intelligence in ant colonies. So, without further delay, over to you, Kelsey.
Thank you so much for that introduction. And I'm so happy to be here. Obviously, I wish I could be there in person to meet you all, but thank you very much for coming. Yep, I'm Kelsey. I'm finishing up my PhD in just the next couple of months, actually. And today I'm very excited to talk to you about work we've been doing on reverse engineering core aspects of human intelligence and how we're trying to incorporate some of those insights to make more general purpose, flexible AI. So a large chunk of my PhD has focused on one particularly impressive facet of human intelligence, which is tool use and tool creation. Why? Well, one reason is that humans are the most advanced tool using and tool creating species in the world. For example, this artificial heart was made by some of humanity's most sophisticated tool creators after many years of experience. And we're experiencing that a lot more now, obviously, with things like ventilators, which are really key to keeping people alive. Um, but even if we're not all as skilled as those medical engineers, tool use and tool creation is still actually universal across human history, with all known cultures having developed physical tools for hunting, crafting, as well as various other kinds of cultural rituals. And tool use and tool creation is seen even in our youngest children. I like this particular fun video of a kid trying to get an Easter egg off the top of that power box, and he immediately figures out that he can sort of repurpose a shovel and tries to use it to reach that out of reach Easter egg in a variety of different ways with many different kinds of failures, even trying both different ends of the shovel in order to try to be successful. But unfortunately, he takes a little bit too long to succeed. I'm going to watch him try one more time. And then just a slightly taller agent, unfortunately, comes in and thwarts his plans. But hopefully he learns something useful about that experience to try next time. And while tool use is quintessentially human, other intelligent species, such as crows, can even craft and creatively repurpose objects in their environment to solve different kinds of physical puzzles, unlike any they would have encountered in the wild, such as this crow who's trying to get a piece of food out of a tube of water by dropping in heavy objects in order to raise the water level. And it demonstrates all kinds of interesting things, like it figures out it needs to have heavy objects, so it just threw that lighter one away, and drops in 3 objects before it is successful. So indeed, tool use is one of our best cross-species intelligence tests in that it doesn't require language, but does require this sort of extended kinds of reasoning. So by comparison, while current machine learning intelligence has made significant progress in recent years, it still lacks some of that flexibility, sample efficiency, and creativity demonstrated by humans and animals, in particular in tool use. For example, while we can now learn a wide variety of different diverse locomotion behaviors with very little prior knowledge, it takes potentially thousands of years of experience to do so. And even after this amount of time, the locomotive behaviors are still not as robust to new obstacles as we might like. Oops. Meta-learning methods similarly have been developed recently that improve our ability to generalize in sample-efficient manners to new test tasks, like those obstacles, but the extent of that generalization sometimes is exceptionally limited, at least in how we often measure it. For example, these two reaching tasks, where a two-joint arm has to reach a point in the plane, don't have significant differences between meta-train and meta-test. The point is simply moved between different locations in a 2D arena, but there are not often systematic looks into how far these things can generalize. Multitask learning has made great strides in achieving human level performance across a wide variety of distinct video games in Atari, perhaps most recently in this paper from Badia et al. In 2020. But millions of frames of experience are required, and generalization outside of those specific training games remains pretty poor. And finally, datasets like Clever have spurred the development of better compositional and neurosymbolic models for combinatorial generalization, but these methods still struggle to discover new compositions like those in a new dataset called Clever Humans, where humans develop their own questions for the domain, even if you use 17,000 examples for fine tuning. So my research resonates with directions that call for learning with more structure. And by structure, I mean the kind of factorized distributions that have been critical to the revolution in vision, where convolutions as a factorization, generally understood as sharing learned parameters across space, led to enormous progress in machine abilities to transform, recognize, and classify visual input. But there are many other ways in which the world is factored. For example, from various developmental research, we believe that the world is composed of objects, and even the youngest children understand what these are. And we know that these objects obey the laws of physics, which governs how they move through space and time. And we know from behavioral and neuroscientific evidence that intelligent animals group their observations into events, such that their experience is not simply an unbroken continuous stream. So my research really aims to incorporate these kinds of factorizations into artificially intelligent agents to make them more like the kinds of natural intelligence we know. So in the first part of the talk, I'll discuss how to harness objects, physics, and events to improve agents' abilities to act. The majority of the talk is going to focus on our work in creative and rapid tool use in humans and how to replicate similar abilities in machines by harnessing object and physical knowledge. I will also talk about two other projects, one which imbues significantly more task-specific knowledge to a robot to allow it to perform tool use tasks involving long sequences of manipulations and dynamic interactions, and one in which I will show how far you can generalize by only incorporating object and relational structure into an agent's policy without the need for any specific physical knowledge. I'll then briefly talk about some of our first steps in discovering discrete structure for classification, plus ongoing and future work to discover compositional structure using these same approaches for modeling physical dynamics and trying to learn different kinds of action representations. So in studying human and biological intelligence, cognitive scientists spend a good deal of time thinking about what kinds of tasks are both ecologically motivated and will elicit sufficiently interesting and complex behavior to analyze. So for this first project, we wanted to look at a task which would require object-oriented representations and reasoning. So we chose a task motivated by an activity adults and children do pretty often, which is to construct things. And this is a nice task because the ceiling on construction expertise is pretty high. Expert human adults create entire cities that can withstand even substantial natural disasters. But the simplest forms of construction also appear in young children playing with blocks, and even birds who regularly construct impressively stable nests from collections of found natural objects like twigs and pieces of cloth. But because machines are still pretty far from successfully doing any of these tasks at the level of complexity of natural intelligence, we introduced this gluing task, which requires stabilizing a given tower of blocks by applying glue. So in this task, people see a tower of between 2 to 10 blocks, and they must click circles which represent the contact points between the blocks in order to apply glue to that contact point with the goal of stabilizing the tower. And the reward structure for this task is that every glue that they use is a point lost, and every block that remains standing after physics is turned on is a point gained. And if you get exactly the optimal configuration of glue, then you get an extra 10 points. So the question then becomes, how should we represent a given block tower in order to do any kind of meaningful learning in this task? So one option would just be to represent the tower in some unstructured way as either, for example, just a concatenated set of features for the different blocks and the different edges, or as an actual image, and pass this to a MLP or a convolutional neural network. But other options are to view the tower as a graph with the vertices representing blocks and the edges representing the possible block interactions. And if you wanted to add even more structure, you could consider a sparse graph where edges only exist between blocks in contact and represent the presence or absence of glue. And the benefit of a graph representation is that it might be preferable since it has the ability to explicitly represent relations between blocks. It can handle block towers of any size, unlike an unstructured MLP. And we might be able to intelligently share representations and policies across blocks and edges to potentially improve our sample efficiency. So now the natural question from that is, how can we actually learn a representation on top of that graph from experience to actually do something like the gluing task? And to do that, we'll turn to a very general technique that has been increasingly used over the past few years called graph neural networks. And graph neural networks have been applied to a variety of graph-based machine learning problems at this point, such as predicting quantum properties of organic molecules, predicting traffic flow through city grids, or predicting the motion of objects in different kinds of physical scenes. I'll just give a brief overview of how graph networks work using the following notation. So we're going to consider graphs consisting of vertices V, edges E, and global properties U, where vertices, edges, and globals can have associated feature attributes. And in the general case, the edges are going to be directed. So that means that they're going to go from some sender node VSK to some receiver node VRK. A graph network is then a transformation of an input graph on the left into an output graph on the right with updated attributes for the edges, vertices, and globals. But critically, nothing is updated about the graph structure itself. We're just going to update the feature values. The most general graph network definition includes learnable functions phi v, phi e, and phi u that transform the vertices, edges, and globals of the graph respectively, as well as a set of pooling functions rho, which could include, for example, the sum, max, or mean, just some kind of aggregation function. A choice of these networks, phi v, phi e, and phi u, as well as pooling functions, instantiates a specific model from the family of graph networks. So the main question for graph networks is then how to make the learnable functions phi dependent on the graph structure. So to do so, the edge function will depend not just on the edge attributes directly, but also on the nodes in which it connects, as well as the global attribute of the graph. And so phi e then is a function of E3 here, V2, V4, and U. And the embedded E3 prime in the higher dimensional space could then represent something like the forces between blocks in the tower. The vertex network similarly needs to take into account graph structure. So to do so, phi v is going to depend again on the current representation V, a pooled representation of all the incoming edges to V, and the global graph attribute. This embedded vector in V2 prime could then represent something like an updated state for the block vertex due to forces from other blocks. And just like the other networks, the global network is going to depend on the current attribute, as well as the pooled edges from the entire graph and the pooled vertices from the entire graph using that aggregation function rho. That embedded global could then be used to learn to represent, for example, the stability of the tower or the energy of the entire system. So what I just showed was how you might go and produce a single update to get new representations for phi for the node, edge, and global attributes of the graph. But you can also run this function multiple times to potentially spread information throughout the graph in order to have non-adjacent nodes still still factor into the update for nodes at various other parts of the graph. So for example, if you consider just V1 here, after one step of updates, the new representation V1 prime is going to depend on V2. But after two steps of updates, it's now going to depend on the representations of all of the different nodes in the graph. And so in this way, you can spread information between vertices instead of just locally. So now that we have that representation, the question is, how can we use it? So we can first consider just the problem of predicting the stability of the tower, which is going to be a global graph attribute. And to do that, we'll look first at a fully connected tower graph and a sparsely connected tower graph to understand whether the added sparsity matters for prediction. We find that in the limit, sparsity doesn't actually matter for the graph representation. Both the sparse and the fully connected graph achieve the same level of predictive accuracy for the global stability attribute in the limit. But we do notice that the sparse graph reaches optimal performance with fewer samples than the fully connected graph, which sort of underscores the general intuition that you probably all have that added structure will improve sample efficiency. But we can also now set up a supervised problem of predicting the points of optimal glue along the edges of a tower. For each tower, there's an optimal gluing, here shown on the left, which sets up an edgewise prediction problem of glue, not glue, for each of these different points of contact. And in this experiment, we were testing whether multiple message passing steps are required to optimally predict glue. And you can get a sense of why that might be necessary by even just considering this glue point here, where it might seem stable locally because this center of mass is supported. But if you consider the rest of the graph, including all of these things on the right-hand side, you can determine that it's not stable and actually has to be glued. So we might expect multiple message passing steps here to be required. And indeed, that is what we find. We find that at least 2 steps of message passing are needed, but we don't actually need more than that in order to do a good job at predicting the optimal glue configuration for a given tower. So a graph is a relational representation, and hopefully you are convinced that you can do prediction with it, given what I just showed you. But you can also set up an RL problem. And what's nice about using this graph representation as the underlying RL representation is that we can now really explicitly get a deeper relational reinforcement learning agent instead of just having a totally unstructured action representational space. So specifically, if your representation is a graph, you can define a relational policy by decoding from the edges of the graph, much like that supervised problem I just showed you. And with this relational policy definition, you can then straightforwardly optimize the graph, the neural network, using Q-learning with experience replay. We can now compare a whole bunch of different models, including our deep relational RL agents, humans, a simulation-based model, and the fully and sparsely connected graph neural networks. I want to note that the RL agents here were trained on 100,000 towers of each size and tested on 15 held-out towers of each size. So we can first look at the total reward achieved by each agent with the dashed line up here, representing the total possible reward across all the test problems. We can first look at human performance. So humans are clearly way below the optimal performance here, but note they did only train on 1 tower of each size. So it would be pretty impressive if they were able to achieve optimal performance. By comparison, if you use a greedy simulation-based agent, which has a true model of the world, it achieves nearly perfect performance, and the only ways in which it fails are situations in which the greedy algorithm does not provide the optimal gluing configuration. But the real question is how well these unstructured MLPs on the left here, the fully connected graph network and the sparsely connected graph network do on the problem. So the unstructured method performs pretty poorly. It performs substantially worse than humans, despite having much more experience. The fully connected graph network, by comparison, does a whole lot better. And the sparsely connected graph network does better still, nearly reaching the simulation-based agent's performance, despite having no direct model of the world. We can additionally look at the performance as a function of the number of blocks, where the MLP is clearly failing pretty much entirely after about 5 blocks. And by comparison, the graph networks do very well, reflecting a general ability to handle combinatorial tasks. We can additionally look even at the generalization by training only on 2 to 6 and 8 to 9 block tower sizes, shown here as the blue bars, and then look at how the performance does for 7 and 10 blocks. So the 7 block condition represents whether or not the agent can interpolate, since it's trained on 2 to 6 and 8 to 9, and the 10 block case tests whether or not the agent can extrapolate, since that's a larger problem size than it has ever seen during training. What's interesting here is that only the sparse graph network both successfully interpolates a policy as well as successfully extrapolating a policy for the 10 block size here, while the fully connected graph is only able to interpolate but not able to extrapolate. So this work was part of a sort of wave on learning dynamics and policies with graph structure that has now become, I think, pretty commonplace. But I just wanted to quickly highlight some of the recent work using graph networks in planning and control. There's some very cool work from the University of Toronto on learning to control complex bodies with joint modeling, as well as some pretty cool stuff from Facebook AI on learning sophisticated forward models for model predictive control, and follow-up work from DeepMind by some of my collaborators on that gluing task, showing that you can use essentially the same model, but decode continuous attributes such as offsets instead of just binary glue indicators from the edges, and this allows you to do even more complex kinds of construction tasks. So to sum up that part of the talk, I just showed that with sufficient experience and the correct relational structure, a physical model is not required to learn a really successful policy. But these models required hundreds of thousands of examples of towers to learn, which obviously isn't practical for either robotics kinds of settings or for trying to model how humans actually interact with the world. So a good question is, how can we learn faster? And the thing I will suggest, which is perhaps obvious, is to use physical models. And because everyone likes some fun videos, I want to give an example of that here, of this crow learning to snowboard. So it did this very cool thing in that it found and repurposed a sort of bottle cap, which it's using here to slide along snow in order to essentially have a good time, as far as we can tell. And it does a bunch of cool things here in that it switches between different kinds of strategies. It first slides on the snow and then it tries sliding without the snow and realizes that's not nearly as fun and switches back. And in the next part of the talk, I'm going to discuss our work to investigate this kind of creative problem solving that we think this crow is demonstrating in making these different strategy switches in both humans and machines. And to do this, we'll need some new set of problems with more variable goals and objects than the gluing task I just showed you. So we're finally going to turn to this general problem of tool use. So tool use, as I sort of hinted at the beginning, has long been of pretty substantial interest to the cognitive science community. It's thought to be one of the defining characteristics of human intelligence, and it's been documented in all known cultures. But studying tool use has been difficult, in part because it requires in-person experiments where people need to manipulate objects. So to get around this, we took inspiration from a popular phone game called Brain It On, which I'm going to demonstrate here, which asks people to draw tools on a screen to accomplish different kinds of goals. And so this is pretty hard. It's a very high dimensional action space that you have to consider. So as a first approximation to this, we built a much simpler game that requires just choosing one particular object from a set of 3, as well as a position to drop it in order to try to accomplish a goal. So in this particular case, someone is trying to get that red ball into the green container. So they first try to hit the red ball directly before realizing that they need to switch to a sort of different strategy, and they try catapulting the ball instead. And they figure out that they didn't catapult it quite hard enough, so they're able to intelligently structure their next action to catapult it, but from higher up. Concurrently to this, another team at Facebook developed an environment called FIRE, which is explicitly designed for comparing and testing the physical reasoning capabilities of deep agents instead of also comparing to humans. And we've just collaborated with their team recently to try to release an environment that attempts to integrate these two settings, which we call OGRE, for object-based generalization and reasoning environment. And if you're interested in any of these, I'd really love to chat further with you. We have a bunch of GitHub repositories for implementing various environments and different kinds of agents, and I would be very curious to see if people have thoughts on how to solve these. So in designing this game, we had 5 central considerations for how we wanted what we wanted to kind of address with this environment. The first is that we wanted something where the goals were visually defined instead of requiring text like in Brain It On or in things like Clever. We wanted a game where physical reasoning would be necessary to succeed in a sample efficient manner. with a richer range of object interactions than things like the gluing task, which I just showed, which include things like complex shapes, as well as gravity and elasticity and all kinds of things. And we wanted a game in which there would be many different problems, but with one shared dynamics and action space, such that agents could generalize between levels by learning the dynamics or learning action priors. And finally, we wanted to make sure that this task was actually a good example of human tool use in that it elicits few-shot trial and error learning in humans. So why are these tasks challenging? Several of the levels involve intervening on dynamical systems rather than assuming everything is quasi-static. In robotics, this is somewhat unusual, and many of the best methods from classical robotics do not obviously generalize to this setting. The action space is very large. We have a continuous position plus a choice of tools, and the reward is sparse, which is always a problem in reinforcement learning. If you wanted to do model-based RL, which would be the obvious candidate for this, you'd have to make a very good model that could make accurate long horizon predictions through complex shapes and contacts. And finally, there's a pretty central question here of what can even be transferred between tasks at all, because meta learning in this richer problem space will likely yield very different insights about flexibility than previous environments where there's a lot more similarity between the different kinds of tasks. So to give you a sense of the richness of the problem space, these are 20 levels from the tools game, and they're designed to cover a wide variety of different physical concepts, objects, and strategy types. So some levels require creative thinking about how to move something you can't hit directly, such as that catapulting level, or others like Towers B, where that red block that's relatively small in the right-hand corner can't be directly reached, so you have to figure out how to topple it by toppling other blocks around it. Other levels require creating a support, like in table A, where you have to support this plank that's falling by placing something underneath it so that the ball can roll across the top and into the goal. And as a further test of generalization, we design these match level pairs with minimal differences that have a large impact on which tools will be successful. For example, shafts A and shafts B are exactly the same level, except that they differ by whether or not one of the two balls that represents an easier strategy is covered by a block, which means you can no longer hit that ball directly. And we expect these to be particularly difficult levels for image-based machine learning agents, since these changes are relatively small relative to the rest of the scene. So I want to again show you some fun examples of how people play this game. On the left, this participant first tries to hit the ball directly by choosing a sort of large blank object. And obviously that doesn't work, but they do a classic thing that people do frustratingly, which is to try almost exactly the same thing again. But after a couple of failures there, they figure out after some thinking, the sort of right general strategy of thing, which is to support this table and eventually fine tune that to allow the ball to roll across the platform and into the goal. And this level on the right is even harder. I encourage you to think about how you might solve this, but this participant is trying to essentially hit the ball in whatever way they can. They hit it here, but while it might be very tempting to think that this is going to go into the goal, it's not fast enough. And so that's frustrating to accomplish. They try, several other things to try to hit the ball directly, various moves. And then they finally have this insight that there's sort of an interesting dynamical thing that happens there, which is that that hook, if dropped on the platform, will hook around, imparting enough momentum to the ball so that it rolls into the goal. And I show you these examples to point out that people are not perfect from the beginning at these kinds of tasks. They require this sort of structured trial and error learning, as well as some kinds of aha moments of insight for how to choose the right qualitative strategy to then fine tune it to be successful. So we propose a model to capture this behavior of people in this game based on task general structure that we think is pretty important for creative tool use in humans. Specifically, we call this model sample simulate update, or SUP, in that it samples structured object-oriented actions to interact with the scene. It checks these samples by using an imperfect internal simulation engine, and it updates its beliefs about good actions to take based on these noisy simulations and failures it makes in the real world. And a central cognitive tenet that this model has is that we're presuming that people are updating model-based strategies, not their particular physical models, with the intuition that people already have fairly good models of physics, and they instead need to learn how to use those models effectively for one particular level. So SUP's initial beliefs about good actions are based on its object-oriented prior, and it updates these through simulation and action using a proxy reward function. The reward function that we use is the difference your action made to the scene rather than just how close you got to the goal. And this ends up being important for capturing interventions on dynamical scenes where things could already be moving before you actually do anything at all. Our exploration policy here is also structured, and that ends up being very important. It samples actions relative to objects in the scene relationally instead of just absolute positions. And those two ingredients, the structured exploration and the proxy reward, allow this model to converge on pretty good solutions with only a few simulations and actions for any given problem. So in order to measure that, we tested the model against humans in an online task where each participant played 14 levels of the original tools game, and we record their tool choices and placements. We can at least first coarsely look at just how many attempts people take to solve each level, which here is human attempts on the y-axis with how many attempts the model took on the x-axis. And we can also compare how often people solved a level at all, human accuracy here on the y-axis, and how often the model did on the x-axis. In both cases, we see an excellent correlation between people and the model across the 20 levels in the game, suggesting that at least at a course level, this SUP model is capturing human behavior very well. And I also want to note that these results generalize to an extra set of 10 levels that we developed after creating the model and testing hyperparameter sensitivity. But those are pretty coarse measures. So we can even zoom in a little bit to figure out how the model does with respect to people at using something that we call the cumulative solution rate, or the number of participants who solve the level in X attempts. So across the various levels, you can see that the red model line and black human line are actually very well matched, suggesting that it's not just overall accuracy and placement numbers, but the actual solution rates that we're doing a good job of capturing. But we can zoom in even more on just a couple of levels and look at the precise placements used by people in the model. We'll look at 3 examples where the human rate and model rate agree, and one where they do not, this falling level. So visualized here are those attempts with the first and last placements for both humans and our model. First placements in the first row, last placements in the second row, with the color representing the tool that they chose. Between the first tool is pink, second tool is yellow, third tool is blue, as well as where they put that tool. The model's choices are shown as the sort of blobby background colors, and the people's choices are shown as the small points. And we were pretty excited to see these results because the model seems to be capturing this kind of initial multimodal distribution that, that humans show, for example, in Catapult, where they're trying to either hit the ball directly or catapult the ball into the goal, and converges to the same kind of solution as humans, which is to catapult the ball into the goal. But similarly, this also seems to happen for the seesaw level, this prevention level, and then this falling level is the very interesting failure case. People here are actually surprisingly bad, much worse than the model is. And this level is surprisingly easy to solve if you put any object beneath the container so that the container tips over and that the ball falls out. But people are very biased to put something above the container, and therefore took much longer to find a solution, even though they're not biased in that particular way in other levels. For example, Seesaw, where a good number of people place an object underneath that platform. So this suggests that people might be using sort of more interesting contextual priors than what we have included so far in our modeling. To really understand which components of the model are important for predicting human behavior, we can ablate different parts and see how well they fit our human data. We can remove any of the 3 components, the prior, the simulator, or the updating mechanism. And we additionally test 2 alternative models, one in which we use observations to update our estimates of physical parameters, and one inspired by current approaches in AI, i.e. deep image-based reinforcement learning. So the deep image-based reinforcement learning method we use to try to benchmark some standard model-free method on the environment, in part to see whether or not generalizable priors could be learned from a large amount of experience with related but not identical levels. And for these levels, we randomly vary several aspects of each scene, as well as the available tools to produce about 1,000 example levels of each kind of template. If we look at how well each of those models correlates with human accuracy across the levels, we can see that in all cases, the alternatives are much worse than the full model, with the image-based EQN worse than the structured object-oriented approaches, suggesting that it's not learning a generalizable policy. And here are two levels that illustrate why both the object-oriented prior and the updating mechanism are needed. On the left is the bridge level, which is solved by placing the pink object underneath the two planks. And in this case, the problem is mostly search. You just need to have, people don't generally fine tune their actions. They just require some sort of aha moment of insight to figure out that they need to put something underneath these two planks. And here, the ablations and alternative methods that use the structured prior perform much better than methods which do not. By contrast, catapult is one that does require fine tuning, like I showed initially, where people often need to sort of figure out that they need to add more force in order to be successful. And so here, the ablations which include the updating method are much more successful than the ones that do not. So to sum up this part, we suggest that structured model-based strategy learning is underlying rapid trial and error learning in humans. And we contribute an environment for few-shot trial and error learning with human benchmarks, a structured model that explains human behavior in this setting that includes object-oriented exploration, an imperfect physical model, and a counterfactual proxy reward. And we think this opens up a lot of interesting questions for AI and machine learning, i.e. how to learn the structured parts of this SUP model and potentially improve upon it in various ways. So the object-oriented prior, the dynamics models, and better use of observations.
So we have a
Yeah.
question, Kelsey. Koshav, do you want to unmute yourself?
Yeah. So my question was, you showed those kind of 4 different levels and you zoomed in on those about human performance versus the agent's performance.
Yes.
I was specifically interested in one where you showed how the agent performed better due to, humans having this prior notion of placing something above as opposed to below. But I noticed one more graph where the human performed much better than the agent.
Yes.
And I was wondering, what is it that the agent kept missing? Is there some similar type of, insight you have? So I think it's number 13, maybe, is what I was looking at, or 4.
Yeah, there are a few. Yeah. So to go back to this slide, there are a couple here that I can point out. So for example, this number 4 chaining level, that level, if I can get back to it, that level is this one on the bottom left-hand corner. And this level is very challenging because it essentially has a decoy that allows the agent to get pretty high reward without ever being successful. And that is to try to hit this ball on the right into the container. And so in this setting, the agent really gets stuck, essentially trying to do that over and over again, because hitting this ball to knock into this ball to knock into this ball into the goal is substantially less likely under a noisy physics model, which has noise at the collision points. And so it essentially perseverates in a way that people do not seem to perseverate within this level. And that's a major limitation. In the prevention cases, it's a sort of similar story in that having this noisy physical model means that in these cases where these are the 2 prevention levels here, you need to essentially take a very precise placement to make sure that this block does not fall down this shaft and block this ball. But many of the precise placements are just difficult to find in doing essentially just object-oriented sampling. And so it ends up searching far more and just getting stuck in a timeout. So it's only allowed like 5 simulations before it has to act. And it essentially does not find solutions within those 5 simulations. And as a result, just takes bad actions. So those are 2 ways in which this agent is not being human-like, and I'll show a couple more on the next slide. Does that make sense?
Yep, thank you.
Okay. So yeah, so there are also several other limitations sort of inspired by that. One is that, so even with the object-oriented prior, there are obviously situations in which that's not going to allow you to succeed just having a sampling-based kind of framework. So in this level, it seems perhaps pretty immediately obvious that you need to take this block and plug this hole, but that's a super specific placement that you need to make. And so you're very unlikely to find that by just sampling and then running your dynamics model forwards. You also need to be smarter about when to switch strategies, which I mentioned for that chaining level, but also comes up in very similar levels like these, where in order to catapult this object into the goal, you need to choose the heaviest tool. And there's a very small region up here that you can drop it from. And the much more successful thing to get higher reward is just to try to hit this ball directly into the green area. And so it gets stuck there. And sort of more generally, to hint at some of the robotic stuff I'm going to talk about next, forward rollouts in general may still be insufficient for planning, especially if you have more complex long-range processes like more common manipulation-based tool frameworks where you might need to use a hook to get another hook to get a ball, for example. So what we'll do instead is in the next project, I'll talk about something we collaborated on with Marc Toussaint to determine what would be required to make robotic agents able to perform the same kinds of tool use tasks that natural intelligences do. So for this, we developed a method that falls under the general umbrella of task and motion planning, which is a hybrid multi-level approach to planning, which breaks the planning problem into 2 steps. In the first step, which is task planning, a task tree is constructed which consists of the high-level actions, also sometimes called modes, that can be taken from any state. And each of these modes is a symbol, like grasp, shown here on the left, but it's a symbol that takes typed objects as input and is additionally parameterized by continuous variables, such as the angle or force of the grasp. It's therefore often referred to as a hybrid representation, i.e. a mixture of discrete and continuous variables. So here's an example task tree for the problem on the right. In the first step, you could try to grasp the hook or the ball. Given that you grasp the hook, you could try to push the ball with the hook, hit the ball with the hook, or pass the hook back to your other hand. This then leads to more options and so forth until you reach the goal. So finding a plan then amounts to choosing a branch through the search tree and optimizing for a specific path that satisfies the differentiable constraints implied by those high-level actions along that branch, i.e. choosing the parameters theta for each of those different symbols that you've chosen. If that doesn't work, i.e. you can't find a path or a setting of these parameters theta that allows you to get from the start state to the goal, then you have to try a different sequence of symbols through this tree and optimize again. And doing this results in a diverse set of paths that will allow a robot to achieve its goal, such as shown here on the right. So it might be the case that you can have multiple paths through this tree that each result in feasible specific dynamic trajectories that you can accomplish. And so you can have a multitude of different strategies that are successful. So here's just some examples of how that works in practice for a robot acquiring an object in various different ways. And what's nice is that it's, pretty impressive long-range interactions, but one obvious limitation, which I think we'll get to in the next slide, and even here, is that it does things that seem just very physically unrealistic, like very wishful thinking. This being perhaps the strongest example of it, where it pushes this onto a piece of paper and then magically rotates that paper without having the ball move, almost as if the ball and the paper were made of Velcro in order to get the ball into the hand. So it's impressive in that it can accomplish things that many other methods can't. But since it's not doing any learning, it's in some sense maximally sample efficient, but this comes at the cost of adaptivity and robustness. And obviously those adaptivity and robustness are key markers of the ways in which natural intelligent agents respond to problems. And so for another fun video, you can consider this crow that's again trying to get something out of a tube of water, but this time this tube is actually too wide, and it realizes that after dropping in 2 objects, so it's able to switch to the narrower tube, where every object that's dropped in is going to raise the water level more. But the fact that it switched suggests that it didn't have perfect physical knowledge, right? Like otherwise it would have done the correct thing originally, potentially. And so the big question is, how do we take some of the best aspects of task and motion planning, but then try to make it more adaptive and robust? And the way I'm going to propose next is some initial steps we've been doing in that direction to try to learn these hybrid action modes based on experience. And that would be very valuable if we could do that, because it would ensure that the modes that we learn actually reflect the physical world in which they're used, as well as only representing the kinds of tasks the agent actually needs to accomplish within its environment. So I'm now going to get into just this last quick part of the talk, where I'll show you a very general technique we've developed called infinite mixture prototypes, which we initially used to discover task-specific mixed discrete continuous structure for the problem of few-shot classification. I'll then show you super briefly how this same technique can be used to learn structure for dynamics modeling, including naturally discovering different kinds of ways in which an agent can interact with the scene. So infinite mixture prototypes combine two key ideas, deep representation learning and infinite mixture modeling, for inferring variable numbers of clusters within a feature space. And critically, we learn the deep embedding jointly with the clustering process, such that the embedding learns to be useful for the task of non-parametric clustering-based classification. And this is unlike previous approaches to few-shot learning via clustering, such as prototypical networks on the left and deep nearest neighbors on the right, which are both previous models that have been applied to this task. Infinite mixture modeling allows us to naturally adapt between these very simple representations that only have a mean or a single cluster for a single class, and nearest neighbors, which are very complex but potentially computationally expensive. Infinite mixture prototypes are able to figure out whether or not they need to be simple or complex by discovering the multimodal class structure that best supports the task loss. And in this case, that's going to be classification. So using infinite mixture prototypes lets us do a really good job of discovering subcategory structure like characters from supercategory training like alphabets or superclasses. And so what's really cool is that we can train on just supercategory labels, like alphabet labels for the omniglot dataset, for example, and then test on character recognition without doing any fine tuning. All we're doing is now changing the clustering. All we're doing is now clustering in the space and trying to use the clusters to predict characters. And what's really impressive is that prototypical networks really don't do very well at this task, but the infinite mixture prototypes do pretty much as well as they would have done if they had been trained directly for the task of character recognition instead of alphabet recognition. And even more impressively to me, this also generalizes to just using super categories on ImageNet, using this tiered ImageNet dataset. So again, we train on just super category information and test on subcategory recognition, and we do pretty much as well as subcategory recognition directly. So how might we use this approach to learn task structure for dynamics modeling? Just like in the first part of the talk, we could go back and consider a tower of blocks that we could slide along a table or pick up. And we might like to learn that we have two kinds of actions we can do, i.e. we could pick up blocks or we could slide them along the ground, as well as the dynamics model to predict how these are actually going to affect the states of the blocks. So this is just like our classification domain, but with a different loss function and potentially something new to cluster. So here we're going to represent the tower as a graph again with an added gripper node up here to represent the robot's interaction with the tower. The updated vertices will now represent the next state predictions for the blocks in the tower, which are all going to depend on this EG prime representation from the gripper. And what we're going to do now is actually cluster the EG prime to try to discover different modes of gripper interactions with the blocks, with the task loss being the next state prediction now instead of classification. And we applied this in two domains. This is all very preliminary work, so I'd be excited to talk about it with people later if they're interested. The first is a 2D domain in which the agent can either slide or pick up blocks in this 2D world. And what we find is that The infinite mixture prototypes does a really good job of discovering exactly two kinds of actions, sliding or picking up, as well as doing a much better job at predicting how those are going to affect the states of the environment. And similarly, we can do it in a more complex 3D environment, where here you can only push blocks around a table, but you can have stable pushes or unstable pushes, and the infinite mixture prototypes are able to successfully discover those two kinds of actions, as well as showing, again, a general relative improvement over methods without modes. So as we continue to work on this, we've been thinking about how to apply infinite mixture prototypes to some of the most exciting benchmarks to me being developed for testing meta-learning and few-shot learning methods. For metadata set, we've been working on hierarchical extensions to infinite mixture modeling to model data sets as well as classes. For the tools game, we've been applying infinite mixture prototypes to learn object-oriented physical strategy concepts like catapulting or support that will hopefully generalize to new objects and new scenes more effectively and allow for improved action sampling. And for Meta World, a benchmark for skill learning, we're working on extending contextual reinforcement learning to by meta-learning discrete mixtures of context variables that will hopefully improve sample efficiency. So to conclude, moving towards more general flexible AI is going to require both improvements to our benchmarks of intelligence, as well as our models for addressing these benchmarks. And today I showed you examples of each. So to make more general and flexible agents, we developed deep relational policies with graph networks to tackle new construction-inspired tasks. To better test the problem solving and sample efficiency of humans and machines, we developed a cognitively inspired tool use benchmark and demonstrated that an agent that had objects, physics, and modes could do particularly well at this benchmark. With the aim of building more capable tool-using robots, we developed a planning method that can take advantage of physical knowledge in the form of hybrid symbols to solve long-horizon dynamic tasks. And finally, with an eye towards models that can discover structure from experience, we combined infinite mixture modeling with meta-learning to improve compositional generalization in the settings of classification and dynamics modeling. So going forwards, there's still obviously much work to be done in reaching the capabilities of this last video agent who does something that we hope kids are maybe not doing too much in lockdown, which is escaping from their area by using a lock hit to open a gate. And obviously this agent is more clever than any of the ones that I've shown today, but to get there, we're doing a variety of things at the moment. First, we'd like to make our tool using agents as adaptive and robust as this child by meta-learning refinements of physics, modes, and policies with respect to specific tasks we'd like our agent to accomplish, like we did with the infinite mixture modeling. Second, we're working to discover hybrid action modes like pull open the gate with object and force, such that they can be reused for new tasks, like pulling with more force or using an unusual object like a locket instead of a hand to open the gate. And to this end, we've been applying infinite mixture prototypes to the context of action representation learning, very much inspired by some of the work that's happened at UMass Amherst over the last couple of years. And third, we'd like to relax our supervision for physical models such that we don't need to know the exact dynamics of chains in order to construct a plan that still uses a chain in an interesting way. And we think that accomplishing these goals will require making use of task general structure like objects, physics, and modes, but adapting it to task-specific requirements like getting an out-of-reach object or escaping quarantine. And I believe the path to do this is by learning hybrid models specifically as a potential framework wherein we might transfer discrete task general structure, but learn these continuous task-specific components such that we can condense very rich world knowledge to actionable plans in the moment. So thank you to all my collaborators on these projects, a variety of different people who have been very inspirational, as well as funding resources, and obviously an absolute enormous thank you to you guys for inviting me here. I wish I could be there in person, but I'm really excited to talk to you all. So thank you again for having me.
Thank you so much, Kelsey. Let's all unmute ourselves and thank the speaker before we move to questions. Okay, awesome. So we have time for questions. If people have questions, put them in the chat, raise your hands. Yeah. So yeah, we have about 5-10 minutes for questions. Okay. Michael.
Hi. First, I want to say that your work is amazing, and this is literally why I got into machine learning. This kind
Oh, thank you.
of figuring out better structures. I'm happy structural relational learning is having a renaissance.
Me too.
I was in particular curious about two things. The first was what was the actual embedding of the physical environment from the tool game? What
Mhm.
was the initial input for that? Was that full image, or did you do a graph representation with some hard-coded relations?
So for that, we actually were using like the object representations instead of the image representations. We tried, so the DQN that I mentioned that we trained was using image-based representations, but we've also tried essentially the same graph network type model that I talked about at the beginning of the talk on the environment. The graph network thing definitely does better, but it's still not doing human-like levels of sample efficiency here. And we think that this is probably because the training environments are just not diverse enough. Like the tasks are all so different that it's kind of hard to pick up on policies that are generalizable. And we can't, it's very hard to learn dynamics models that are sufficiently predictive over like 100 time steps for them to actually be useful. But I think that that's a super promising way to go in the future. And that's sort of what we've been pushing on. But yeah, so not image-based representations. I will say that in that particular case, you could do some very dumb things to just pre-process to get objects, right? Which is to just threshold pixel colors. So it's not particularly interesting from an image processing point of view, but you could also make it arbitrarily more complex to make it more interesting. That was just not the focus of that particular environment.
Sure. I have a follow-up question, if you don't mind.
Yes,
And
of course.
that is, it is my personal opinion that a lack of structure is why sample efficiency is terrible.
Yep.
And one of the most challenging things about machine learning is all this engineering work we're putting into finding the right structures, whether that's over time, whether that's finding not just new features or concepts, but new ways of linking together concepts. So this would be another type of relationship, for example.
Yep.
What do you have any ideas or thoughts of where the next few, where how relations may be learned automatically? So, for instance, humans have a bunch of built-in relations we figured out, like outline matching for that problem you mentioned. It's just a tool we figured out on our own. What are some thoughts you might have on where that could go in the future?
Yeah, it's a great question. The stuff that we've been working on is sort of along two prongs. One is imagining that if you have better relational structure, that will lead to better predictive mechanisms. So in some of the work I mentioned right at the end with the infinite mixture modeling, we've been trying to imagine clustering as giving us information about what kinds of sort of qualitatively different relations might exist that help you essentially better predict the future. So we've seen some promising results there. The other approach we've been taking in Josh's lab more generally, and this is not stuff I talked about here, but it's stuff we've been working on, is to use methods from program synthesis to try to essentially imagine that relations can come from programs, and we can try to synthesize programs that are going to give us relations that when combined with like a graph neural network, for example, give very good predictive performance or very sample efficient agents or what have you. So there's a couple of different citations on those that I could send you. If you email me, I'd be happy to share.
Yes, absolutely. Is your email available?
I think so. I hope so.
On the,
I guess Kalpesh knows, but
Yeah, I mean, I can share it on the chat. I can share your email ID on the chat in a minute. Yeah.
Thank you. I'm sure I could just keep asking questions. But if you have any time for an additional one-on-one that wasn't planned, I'd be grateful. If not, sure. But thank you.
yeah, absolutely. I think there are still slots in the schedule unless things have changed.
So we had a couple of more slots. We have one at 2:30 to 3, and then we have one later in the day at 4:30. So
2:30 to 3 would be amazing. Thank you very much.
Okay, fantastic. If you could like drop your email ID, Michael, then I'll just send over the details to you.
All right, sent.
Okay, fantastic. I'll
And
just
thank you for your talk.
I'll send them over. Send them over after the talks.
Thank
Then.
you. Thank you for your questions.
Okay. Does anyone else have any questions? So I had a question about the tool games environment. I had a couple
Mhm.
of questions there. I was wondering how you collected those levels. I found many of those tasks very fascinating. I was just curious, like, did you like automate it or did you? Uh,
We designed all of them.
oh,
Yeah, that
awesome,
was
awesome, awesome.
yeah. It's a particularly interesting aspect of being a cognitive scientist, I guess. We have to design fun levels, or people won't play the game.
I see, I
um,
see.
but yeah, so yeah, there are also. I guess I don't have a link for it here, but I can add one. But if you just go to, do I have access to the chat? Oh, there it is.
Yeah.
Yes. I think it's, let me just stop my share for a second
Sure,
and I
sure.
will double check. But the games are all playable. There should be, okay, I'm gonna send that to you offline actually. But anyway, we
Okay,
have
okay.
like essentially, I guess 30 to 40 different levels now.
Awesome, awesome.
And they're all inspired by that Brain It On game, but a lot of
Mm-hmm.
the things that we came up with had to be different from that because
Mm-hmm.
they have things like magnets and we didn't want to add magnets. Um, but yeah, it's very interesting to see how people perform. And we've done a bunch of follow-up experiments looking at, for example, we have a cool collaboration with some people in the UK who study individuals with only one hand. And it
Mm-hmm.
turns out that they play these games very differently from people with two hands.
Mm-hmm.
Um, and we've been looking at how people learn within specific types of levels. So if you learn how to catapult something, can you like
Mm-hmm.
flexibly reuse that in different settings? And like, yes, you can combine it with new models. We've been doing a bunch of different kinds of those program synthesis techniques to try to figure out like relational strategies that describe how people generalize across different levels and stuff. But yeah, if you just ping me, I will send you a link offline to check it out. Because yeah, I think they're fun, and I would be super happy if people would start trying to train better agents than a DQN
Mm-hmm.
on them.
Sure, sure. That sounds awesome. So I had one more question. I'll just wait if anyone else wants to ask anything else. You can raise your hands or put it in the chat or just unmute yourself, even that's fine. Um, okay, cool. So I'll just ask it anyway. So I was also wondering in your tool games environment, like, did you encode the natural language sentence as well, or like did you investigate that angle at all, like whether that helps in generalization in some way or something?
We have not, but that's
Okay.
something I'm super curious about. The closest thing we've done recently, it's ongoing, is that we've been asking people to essentially give hints about how to play levels to
Mm-hmm.
other people and figuring out like what kinds of language they use and potentially like doing an embedding of that. There was a cool paper from a group at Salesforce, I think, that I think they called it Esprit, ESPRIT, that looked at natural language descriptions of trajectories within that fire environment that I mentioned as a pretty similar thing.
Yeah, yeah.
And there they said they were able to do a pretty good job at like generating natural language descriptions of trajectories that would be successful based
Mm-hmm.
on quite a bit of input data. But I think they had to make some assumptions about, like, for example, pulling out all the points of contact and only using those to try to describe language and that kind of stuff. So I
Right,
think
right.
there would be room to explore sort of more automated from images without those pre-processing techniques, kinds of things for both describing successful trajectories and also describing goals, which I think would be very cool.
Yeah, it sort of reminds me of the like the clever and NLVR environments a bit,
Yep.
but I think those are just classification settings, if I remember correctly, or or some kind of QA settings, and you don't really interact with the environment and like try to figure something out. So
exactly. Yeah, I know that, for example, the Facebook team, one of their motivations for making that fire environment was basically clever with interaction.
okay.
So yeah, I think noticing that commonality is very reasonable, and it exists. Yeah.
Right. Okay, awesome. So I'll just ask once again, does anyone have any questions? We can take, I think, one more question. Okay, let's all unmute ourselves once again and thank the speaker.
Thanks, everyone. Thank you so much for coming.
Yeah, so I'll just stop the recording.